20 This also means that if your MFU is already maxed out, speculative decoding makes less sense. Figure 9.9. A draft model generates a sequence of K tokens, and the main model accepts the longest subsequence that it agrees with. The image is from blockwise parallel decoding for deep autoregressive models, Stern et al., 2018. If all draft sequences are rejected, the target model must generate the entire response in addition to verifying it, potentially leading to increased latency. However, this can be avoided because of these three insights. 1. The time it takes for the target model to verify a sequence of tokens is less than the time it takes to generate it, because verification is parallelizable, while generation is sequential. Speculative decoding effectively turns the computation profile of decoding into that of pre-filling. 2. In an output token sequence, some tokens are easier to predict than others. It's possible to find a weaker draft model capable of getting these easier to predict tokens right, leading to a high acceptance rate of the draft tokens. 3. Decoding is memory bandwidth bound, which means that during the coding process, there are typically idle flops that can be used for free verification. 20 Acceptance rates are domain-dependent. For texts that follow specific structures like code, the acceptance rate is typically higher. Larger values of K mean fewer verifying calls for the target model but a low acceptance rate of the draft tokens. The draft model can be of any architecture, though ideally it should share the same vocabulary and tokenizer as the target model. You can train a custom draft model or use an existing weaker model. Inference optimization, 429. For example, to speed up the decoding process of Chinchilla 70B, DeepMind trained a 4B parameter draft model of the same architecture, Chin et al., 2023. The draft model can generate a token 8 times faster than the target model, 8 milliseconds per token compared to 1 millisecond per token. This reduces the overall response latency by more than half without compromising response quality. A similar speedup was achieved for T5XXL, Leviathan et al., 2022. This approach has gained traction because it's relatively easy to implement and doesn't change a model's quality. For example, it's possible to do so in 50 lines of code in PyTorch. It's been incorporated into popular inference frameworks such as VLLM, TensorRT-LLM, and Llama. CPP. Inference with reference. Often, a response needs to reference tokens from the input. For example, if you ask your model a question about an attached document, the model might repeat a chunk of text verbatim from the document. Another example is if you ask the model to fix bugs in a piece of code, the model might reuse the majority of the original code with minor changes. Instead of making the model generate these repeated tokens, what if we copy these tokens from the input to speed up the generation? This is the core idea behind inference with reference. Inference with reference is similar to speculative decoding, but instead of using a model to generate draft tokens, it selects draft tokens from the input. The key challenge is to develop an algorithm to identify the most relevant text span from the context at each decoding step. The simplest option is to find a text span that matches the current tokens. Unlike speculative decoding, inference with reference doesn't require an extra model. However, it's useful only in generation scenarios where there's a significant overlap between contexts and outputs, such as in retrieval systems, coding, or multi-turn conversations. In inference with reference, lossless acceleration of large language models, Yang et al., 2023, this technique helps achieve 2 times generation speedup in such use cases. Examples of how inference with reference works are shown in Figure 9.10. 430 Chapter 9, Inference Optimization. Figure 9.10. 2 examples of inference with reference. The text spans that are successfully copied from the input are in red and green. Image from Yang et al. 2023, the image is licensed under CC by 4.0. Inference optimization, 431. 21 The Jacobi method is an iterative algorithm where multiple parts of a solution can be updated simultaneously and independently. Parallel decoding. Instead of making autoregressive generation faster with draft tokens, some techniques aim to break the sequential dependency. Given an existing sequence of tokens x1, x2, xt, these techniques attempt to generate xt plus 1, xt plus 2, xt plus k simultaneously. This means that the model generates xt plus 2 before it knows that the token before it is xt plus 1. This can work because the knowledge of the existing sequence often is sufficient to predict the next few tokens. For example, given the cat sits, without knowing that the next token is on, under, or behind, you might still predict that the word after it is the. The parallel tokens can be generated by the same decoder, as in look-ahead decoding, Fu et al., 2024, or by different decoding heads, as in Medusa, Kai et al., 2024. In Medusa, the original model is extended with multiple decoding heads, and each head is a small neural network layer that is then trained to predict a future token at a specific position. If the original model is trained to predict the next token xt plus 1, the kth head will predict the token xt plus k plus 1. These heads are trained together with the original model, but the original model is frozen. NVIDIA claimed Medusa helped boost Llama 3. 1 token generation by up to 1.9 times on their HGX H200 GPUs, Issa et al., 2024. However, because these tokens aren't generated sequentially, they need to be verified to make sure that they fit together. An essential part of parallel decoding is verification and integration. Look-ahead decoding uses the Jacobi method 21 to verify the gen-arret tokens, which works as follows. 1. K future tokens are generated in parallel. 2. These K tokens are verified for coherence and consistency with the context. 3. If one or more tokens fail verification, instead of aggregating all K future tokens, the model regenerates or adjusts only these failed tokens. The model keeps refining the generated tokens until they all pass verification and are integrated into the final output. This family of parallel decoding algorithms is also called Jacobi decoding. On the other hand, Medusa uses a tree-based attention mechanism to verify and integrate tokens. Each Medusa head produces several options for each position. These options are then organized into a tree-like structure to select the most promising combination. The process is visualized in Figure 9.11. For 32, Chapter 9, Inference Optimization. Figure 9.11. In Medusa, Kai et al., 2024, each head predicts several options for a token position. The most promising sequence from these options is selected. Image adapted from the paper, which is licensed under CC by 4.0. While the perspective of being able to circumvent sequential dependency is appeal ing, parallel decoding is not intuitive, and some techniques, like Medusa, can be challenging to implement. Attention mechanism optimization. Recall from Chapter 2 that generating the next token requires the key and value vectors for all previous tokens. This means that the following applies. Generating token xt requires the key and value vectors for tokens x1, x2, xt1. Generating token xt plus 1 requires the key and value vectors for tokens x1, x2, xt1, xt. When generating token xt plus 1, instead of computing the key and value vectors for tokens x1, x2, xt1 again, you reuse these vectors from the previous step. This means that you'll need to compute the key and value vectors for only the most recent token, xt. The cache that stores key and value vectors for reuse is called the KV cache. The newly computed key and value vectors are then added to the KV cache, which is visualized in Figure 9.12. Inference optimization. 433. 22. The number of attention computations for an autoregressive model is O(n)(2). Figure 9.12. To avoid recomputing the key and value vectors at each decoding step, use a KV cache to store these vectors to reuse. A KV cache is used only during inference, not training. During training, because all tokens in a sequence are known in advance, next token generation can be computed all at once instead of sequentially, as during inference. Therefore, there's no need for a KV cache. Because generating a token requires computing the attention scores with all previous tokens, the number of attention computations grows exponentially with sequence length. 22 The KV cache size, on the other hand, grows linearly with sequence length. The KV cache size also grows with larger batch sizes. A Google paper calculated that for a 500B+ model with multi-head attention, batch size 512, and context length 2048, the KV cache totals 3 terabytes, Pope et al., 2022. This is 3 times the size of that model's weights. The KV cache size is ultimately limited by the available hardware storage, creating a bottleneck for running applications with long context. A large cache size also takes time to load into memory, which can be an issue for applications with strict latency. The computation and memory requirements of the attention mechanism are one of the reasons why it's so hard to have longer context. Many techniques have been developed to make the attention mechanism more efficient. In general, they fall into 3 buckets: redesigning the attention mechanism, optimizing the KV cache, and writing kernels for attention computation. 434, Chapter 9, Inference Optimization. Calculating the KV cache size. The memory needed for the KV cache, without any optimization, is calculated as follows: 2 times B times S times L times H times MB, batch size S, sequence length L, number of transformer layers H, model dimension M, memory needed for the cache's numerical representation, e.g., FP16 or FP32. This value can become substantial as the context length increases. For example, Llama 213B has 40 layers and a model dimension of 5120. With a batch size of 32, sequence length of 2048, and 2 bytes per value, the memory needed for its KV cache, without any optimization, is 2 times 32 times 2048 times 40 times 5120 times 2 is equal to 54 gigabytes. Redesigning the attention mechanism. These techniques involve altering how the attention mechanism works. Even though these techniques help optimize inference, because they change a model's architecture directly, they can be applied only during training or fine-tuning. For example, when generating a new token, instead of attending to all previous tokens, local windowed attention attends only to a fixed size window of nearby tokens, Beltagi et al., 2020. This reduces the effective sequence length to a fixed size window, reducing both the KV cache and the attention computation. If the average sequence length is 10,000 tokens, attending to a window size of 1,000 tokens reduces the KV cache size by 10 times. Local windowed attention can be interleaved with global attention, with local attention capturing nearby context. The global attention captures task-specific information across the document. Both cross-layer attention, Brandon et al. 2024, and multi-query attention, Shazir, 2019, reduce the memory footprint of the KV cache by reducing the number of key-value pairs. Cross-layer attention shares key and value vectors across adjacent layers. Having 3 layers sharing the same key-value vectors means reducing the KV cache 3 times. On the other hand, multi-query attention shares key-value vectors across query heads. Inference optimization, 435. Grouped query attention, Ainsley et al., 2023, is a generalization of multi-query attention. Instead of using only one set of key-value pairs for all query heads, its grouped query attention puts query heads into smaller groups and shares key-value pairs only among query heads in the same group. This allows for a more flexible balance between the number of query heads and the number of key-value pairs. Character AI, an AI chatbot application, shares that their average conversation has a dialogue history of 180 messages, 2024. Given the typically long sequences, the primary bottleneck for inference throughput is the KV cache size. 3 attention mechanism designs, multi-query attention, interleaving local attention and global attention, and cross-layer attention, help them reduce KV cache by over 20 times. More importantly, this significant KV cache reduction means that memory is no longer a bottleneck for them for serving large batch sizes. Optimizing the KV cache size. The way the KV cache is managed is critical in mitigating the memory bottleneck during inference and enabling a larger batch size, especially for applications with long context. Many techniques are actively being developed to reduce and manage the KV cache. One of the fastest-growing inference frameworks, VLLM, gained popularity for introducing paged attention, which optimizes memory management by dividing the KV cache into non-contiguous blocks, reducing fragmentation, and enabling flexible memory sharing to improve LLM serving efficiency, Quan et al., 2023. Other techniques include KV cache quantization, Hooper et al., 2024, Kong et al., 2024, adaptive KV cache compression, Gu et al., 2023, and selective KV cache, Liu et al., 2024. Writing kernels for attention computation. Instead of changing the mechanism design or optimizing the storage, this approach looks into how attention scores are computed and finds ways to make this computation more efficient. This approach is the most effective when it takes into account the hardware executing the computation. The code optimized for a specific chip is called a kernel. Kernel writing will be discussed further in the next section. One of the most well-known kernels optimized for attention computation is Flash Attention, Dao et al., 2022. This kernel fused together many operations commonly used in a transformer-based model to make them run faster, as shown in Figure 9.13. 436, Chapter 9, Inference Optimization. 23 convolution operations are often used in image generation models like Stable Diffusion. Figure 9.13. Flash Attention is a kernel that fuses together several common operators. Adapted from an original image licensed under BSD3 clause. Kernels and compilers. Kernels are specialized pieces of code optimized for specific hardware accelerators, such as GPUs or TPUs. They are typically written to perform computationally intensive routines that need to be executed repeatedly, often in parallel, to maximize the performance of these accelerators. Common AI operations, including matrix multiplication, attention computation, and convolution operation, all have specialized kernels to make their computation more efficient on different hardware. 23 writing kernels requires a deep understanding of the underlying hardware architecture. This includes knowledge about how the memory hierarchy is structured, such as caches, global memory, shared memory, and registers, and how data is accessed and moved between these different levels. Moreover, kernels are typically written in lower-level programming languages like CUDA, for NVIDIA GPUs, Triton, a language developed by OpenAI for writing custom kernels, and ROCm, for AMD GPUs. These languages allow fine-grained control over thread management and memory access but are also harder to learn than the languages that most AI engineers are familiar with, like Python. Due to this entry barrier, writing kernels used to be a dark art practiced by a few. Chip makers like NVIDIA and AMD employ optimization engineers to write kernels to make their hardware efficient for AI workloads, whereas AI frameworks like Inference Optimization, 437. PyTorch and TensorFlow employ kernel engineers to optimize their frameworks on different accelerators. However, with the rising demand for inference optimization and the ubiquity of accelerators, more AI engineers have taken an interest in writing kernels. There are many great online tutorials for kernel writing. Here, I'll cover 4 common techniques often used to speed up computation. Vectorization. Given a loop or a nested loop, instead of processing one data element at a time, simultaneously execute multiple data elements that are contiguous in memory. This reduces latency by minimizing data I/O operations. Parallelization. Divide an input array, or n-dimensional array, into independent chunks that can be processed simultaneously on different cores or threads, speeding up the computation. Loop tiling. Optimize the data accessing order in a loop for the hardware's memory layout and cache. This optimization is hardware dependent. An efficient CPU tiling pattern may not work well on GPUs. Operator fusion. Combine multiple operators into a single pass to avoid redundant memory access. For example, if 2 loops operate over the same array, they can be fused into one, reducing the number of times data is read and written. While vectorization, parallelization, and loop tiling can be applied broadly across different models, operator fusion requires a deeper understanding of a model's specific operators and architecture. As a result, operator fusion demands more attention from optimization engineers. Kernels are optimized for a hardware architecture. This means that whenever a new hardware architecture is introduced, new kernels need to be developed. For example, Flash Attention, Dow et al., 2022, was originally developed primarily for NVIDIA A100 GPUs. Later on, Flash Attention 3 was introduced for H100 GPUs, Shaw et al., 2024. A model script specifies a series of operations that need to be performed to execute that model. To run this code on a piece of hardware, such as a GPU, it has to be converted into a language compatible with that hardware. This process is called lowering. A tool that lowers code to run a specific hardware is called a compiler. Compilers bridge ML models and the hardware they run on. During the lowering process, whenever possible, these operations are converted into specialized kernels to run faster on the target hardware. 438 Chapter 9, Inference Optimization. Inference Optimization Case Study from PyTorch Figure 9:14 shows how much throughput improvement the PyTorch team could give to Llama 7b through the following optimization steps. PyTorch, 2023-1. Call torch. Compile to compile the model into more efficient kernels. 2. Quantize the model weights to int8. 3. Further quantize the model weights to int4. 4. Add speculative decoding. Figure 9:14. Throughput improvement by different optimization techniques in PyTorch. Image from PyTorch, 2023. The experiment was run on an A100 GPU with 80 GB of memory. It was unclear how these optimization steps impact the model's output quality. Inference optimization, 439. 24 Many companies consider their kernels their trade secrets. Having kernels that allow them to run models faster and cheaper than their competitors is a competitive advantage. Compilers can be standalone tools, such as Apache TVM and MLIR, multi-level intermediate representation, or integrated into ML and inference frameworks, like Torch. Compile, a feature in PyTorch, XLA, Accelerated Linear Algebra, originally developed by TensorFlow, with an open-source version called OpenXLA, and the compiler built into the TensorRT, which is optimized for NVIDIA GPUs. AI companies might have their own compilers, with their proprietary kernels designed to speed up their own workloads. 24 Inference Service Optimization. Most service-level optimization techniques focus on resource management. Given a fixed amount of resources, compute and memory, and dynamic workloads, inference requests from users that may involve different models, the goal is to efficiently allocate resources to these workloads to optimize for latency and cost. Unlike many model-level techniques, service-level techniques don't modify models and shouldn't change the output quality. Batching. One of the easiest ways to reduce your cost is batching. In production, your inference service might receive multiple requests simultaneously. Instead of processing each request separately, batching the requests that arrive around the same time together can significantly reduce the service's throughput. If processing each request separately is like everyone driving their own car, batching is like putting them together on a bus. A bus can move more people, but it can also make each person's journey longer. However, if you do it intelligently, the impact on latency can be minimal. The three main techniques for batching are static batching, dynamic batching, and continuous batching. The simplest batching technique is static batching. The service groups a fixed number of inputs together in a batch. It's like a bus that waits until every seat is filled before departing. The drawback of static batching is that all requests have to wait until the batch is full to be executed. Thus the first request in a batch is delayed until the batch's last request arrives, no matter how late the last request is. 440 Chapter 9, Inference Optimization. Dynamic batching, on the other hand, sets a maximum time window for each batch. If the batch size is 4 and the window is 100 milliseconds, the server processes the batch either when it has 4 requests or when 100 milliseconds has passed, whichever happens first. It's like a bus that leaves on a fixed schedule or when it's full. This approach keeps latency under control, so earlier requests aren't held up by later ones. The downside is that batches may not always be full when processed, possibly leading to wasted compute. Static batching and dynamic batching are visualized in Figure 9.15. Figure 9.15. Dynamic batching keeps the latency manageable but might be less compute efficient. In naive batching implementations, all batch requests have to be completed before their responses are returned. For LLMs, some requests might take much longer than others. If one request in a batch generates only 10 response tokens and another request generates 1,000 response tokens, the short response has to wait until the long response is completed before being returned to the user. This results in unnecessary latency for short requests. Continuous batching allows responses in a batch to be returned to users as soon as they are completed. It works by selectively batching operations that don't cause the generation of one response to hold up another, as introduced in the paper Orca, Yu et al., 2022. After a request in a batch is completed and its response returned, the service can add another request into the batch in its place, making the batching continuous. It's like a bus that, after dropping off one passenger, can immediately pick up another passenger to maximize its occupancy rate. Continuous batching, also called in-flight batching, is visualized in Figure 9.16. Inference optimization, 441. Figure 9.16. With continuous batching, completed responses can be returned immediately to users, and new requests can be processed in their place. Decoupling prefill and decode LLM inference consists of two steps, prefill and decode. Because prefill is compute-bound and decode is memory bandwidth-bound, using the same machine to perform both can cause them to inefficiently compete for resources and significantly slow down both TTFT and TPOT. Imagine a GPU that is already handling prefilling and decoding near its peak computational capacity. It might be able to handle another low computational job like decoding. However, adding a new query to this GPU means introducing a prefilling job along with a decoding job. This one prefilling job can drain computational resources from existing decoding jobs, slowing down TPOT for these requests. One common optimization technique for inference servers is to disaggregate prefill and decode. DIST-serve, Zhong et al., 2024, and Inference Without Interference, Hu et al., 2024, show that for various popular LLMs and applications, assigning prefill and decode operations to different instances, e.g., different GPUs, can significantly improve the volume of processed requests while adhering to latency requirements. Even though decoupling requires transferring intermediate states from prefill instances to decode instances, the paper shows communication overhead is not substantial in modern GPU clusters with high bandwidth connections such as NVLink within a node. 442, Chapter 9, Inference Optimization. 25 talks mentioning the prefill to decode instance ratio include Llama Inference at Meta, 2024. The ratio of prefill instances to decode instances depends on many factors, such as the workload characteristics, e.g., longer input lengths require more prefill compute, and latency requirements, e.g., whether you want lower TTFT or TPOT. For example, if input sequences are usually long and you want to prioritize TTFT, this ratio can be between 2:1 and 4:1. If input sequences are short and you want to prioritize TPOT, this ratio can be 1:2 to 1:1. 25 prompt caching. Many prompts in an application have overlapping text segments. A prompt cache stores these overlapping segments for reuse, so you only need to process them once. A common overlapping text segment in different prompts is the system prompt. Without a prompt cache, your model needs to process the system prompt with every query. With a prompt cache, the system prompt needs to be processed just once for the first query. Prompt caching is useful for queries that involve long documents. For example, if many of your user queries are related to the same long document, such as a book or a codebase, this long document can be cached for reuse across queries. It's also useful for long conversations when the processing of earlier messages can be cached and reused when predicting future messages. A prompt cache is visualized in Figure 9.17. It's also called a context cache or prefix cache. Figure 9.17. With a prompt cache, overlapping segments in different prompts can be cached and reused. Inference optimization, 443. 26 While Llama CPP also has prompt caching. It seems to cache only whole prompts and work for queries in the same chat session, as of this writing. Its documentation is limited, but my guess from reading the code is that in a long conversation, it caches the previous messages and processes only the newest message. For applications with long system prompts, prompt caching can significantly reduce both latency and cost. If your system prompt is 1,000 tokens, and your application generates 1 million model API calls daily, a prompt cache will save you from processing approximately 1 billion repetitive input tokens a day. However, this isn't entirely free. Like the KV cache, prompt cache size can be quite large and take up memory space. Unless you use a model API with this functionality, implementing prompt caching can require significant engineering effort. Since its introduction in November 2023 by Jim et al., the prompt cache has been rapidly incorporated into model APIs. As of this writing, Google Gemini offers this functionality, with cached input tokens given a 75% discount compared to regular input tokens, but you'll have to pay extra for cache storage, as of writing, $1.00/1 million tokens per hour. Anthropic offers prompt caching that promises up to 90% cost savings, the longer the cached context, the higher the savings, and up to 75% latency reduction. The impact of prompt caching on the cost and latency of different scenarios is shown in Table 9.3. 26 Table 9.3. Cost and latency reduced by prompt caching. Information from Anthropic, 2024. Use case latency without caching, time to first token, latency with caching, time to first token, cost reduction chat with a book, 100,000 token cached prompt, 11. 5s2. For S, -79%, -90% many-shot prompting, 10,000 token prompt, 1, 6s1, 1s, -31%, -86% multi-turn conversation, 10-turn convo with a long system prompt, 10s2, 5s, -75%, -53% parallelism accelerators are designed for parallel processing, and parallelism strategies are the backbone of high-performance computing. Many new parallelization strategies are being developed. This section covers only a few of them for reference. Two families of parallelization strategies that can be applied across all models are data parallelism and model parallelism. A family of strategies applied specifically for LLMs is context and sequence parallelism. An optimization technique might involve multiple parallelism strategies. 444, Chapter 9, Inference Optimization. 27 During training, the same technique is called data parallelism. Replica parallelism is the most straightforward strategy to implement. It simply attaches multiple replicas of the model you want to serve. 27 more replicas allow you to handle more requests at the same time, potentially at the cost of using more chips. Trying to fit models of different sizes onto different chips is a bin packing problem, which can get complicated with more models, more replicas, and more chips. Let's say you have a mixture of models of different sizes, e.g. 8B, 13B, 34B, and 70B parameters, and access to GPUs of different memory capabilities, e.g., 24 GB, 40 GB, 48 GB, and 80 GB. For simplicity, assume that all models are in the same precision, 8 bits. If you have a fixed number of chips, you need to decide how many replicas to create for each model and what GPUs to use for each replica to maximize your metrics. For example, should you place 3 13B models on a 40 GB GPU, or should you reserve this GPU for one 34B model? If you have a fixed number of model replicas, you need to decide what chips to acquire to minimize the cost. This situation, however, rarely occurs. Often, your model is so big that it can't fit into one machine. Model parallelism refers to the practice of splitting the same model across multiple machines. Fitting models onto chips can become an even more complicated problem with model parallelism. There are several ways to split a model. The most common approach for inference is tensor parallelism, also known as interoperator parallelism. Inference involves a sequence of operators on multidimensional tensors, such as matrix multiplication. In this approach, tensors involved in an operator are partitioned across multiple devices, effectively breaking up this operator into smaller pieces to be executed in parallel, thus speeding up the computation. For example, when multiplying two matrices, you can split one of the matrices column-wise, as shown in Figure 9.18. Tensor parallelism provides two benefits. First, it makes it possible to serve large models that don't fit on single machines. Second, it reduces latency. The latency benefit, however, might be reduced due to extra communication overhead. Inference optimization, 445. Figure 9.18. Tensor parallelism for matrix multiplication. Another way to split a model is pipeline parallelism, which involves dividing a model's computation into distinct stages and assigning each stage to a different device. As data flows through the model, each stage processes one part while others process subsequent parts, enabling overlapping computations. Figure 9.19 shows what pipeline parallelism looks like on four machines. Figure 9.19. Pipeline parallelism enables model splits to be executed in parallel. Figure 9.19 shows a batch can be split into smaller microbatches. After a microbatch is processed on one machine, its output is passed on to the next part of the model on the next machine. 446, Chapter 9, Inference Optimization. While pipeline parallelism enables serving large models on multiple machines, it increases the total latency for each request due to extra communication between pipeline stages. Therefore, for applications with strict latency requirements, pipeline parallelism is typically avoided in favor of replica parallelism. However, pipeline parallelism is commonly used in training since it can help increase throughput. Two techniques that are less common but might warrant a quick mention to illustrate the diversity of techniques are context parallelism and sequence parallelism. They were both developed to make long input sequence processing more efficient, include context parallelism and sequence parallelism. In context parallelism, the input sequence itself is split across different devices to be processed separately. For example, the first half of the input is processed on machine 1 and the second half on machine 2. In sequence parallelism, operators needed for the entire input are split across machines. For example, if the input requires both attention and feed-forward computation, attention might be processed on machine 1 while feed-forward is processed on machine 2. Summary: a model's usability depends heavily on its inference cost and latency. Cheaper inference makes AI-powered decisions more affordable, while faster inference enables the integration of AI into more applications. Given the massive potential impact of inference optimization, it has attracted many talented individuals who continually come up with innovative approaches. Before we start making things more efficient, we need to understand how efficiency is measured. This chapter started with common efficiency metrics for latency, throughput, and utilization. For language model-based inference, latency can be broken into time to first token, TTFT, which is influenced by the prefilling phase, and time per output token, TPOT, which is influenced by the decoding phase. Throughput metrics are directly related to cost. There's a trade-off between latency and throughput. You can potentially reduce cost if you're okay with increased latency, and reducing latency often involves increasing cost. How efficiently a model can run depends on the hardware it is run on. For this REA-Sun, this chapter also provided a quick overview of AI hardware and what it takes to optimize models on different accelerators. The chapter then continued with different techniques for inference optimization. Given the availability of model APIs, most application developers will use these APIs with their built-in optimization instead of implementing these techniques themselves. While these techniques might not be relevant to all application developers, summary 447. Believe that understanding what techniques are possible can be helpful for evaluating the efficiency of model APIs. This chapter also focused on optimization at the model level and the inference service level. Model-level optimization often requires changing the model itself, which can lead to changes in the model behaviors. Inference service-level optimization, on the other hand, typically keeps the model intact and only changes how it's served. Model-level techniques include model-agnostic techniques like quantization and distillation. Different model architectures require their own optimization. For example, because a key bottleneck of transformer models is in the attention mechanism, many optimization techniques involve making attention more efficient, including KV cache management and writing attention kernels. A big bottleneck for an autoregressive language model is in its autoregressive decoding process, and consequently, many techniques have been developed to address it, too. Inference service-level techniques include various batching and parallelism strategies. There are also techniques developed especially for autoregressive language models, including prefilling/decoding decoupling and prompt caching. The choice of optimization techniques depends on your workloads. For example, KV caching is significantly more important for workloads with long contexts than those with short contexts. Prompt caching, on the other hand, is crucial for workloads involving long, overlapping prompt segments or multi-turn conversations. The choice also depends on your performance requirements. For instance, if low latency is a higher priority than cost, you might want to scale up replica parallelism. While more replicas require additional machines, each machine handles fewer requests, allowing it to allocate more resources per request and, thus, improve response time. However, across various use cases, the most impactful techniques are typically quantization, which generally works well across models, tensor parallelism, which both reduces latency and enables serving larger models, replica parallelism, which is relatively straightforward to implement, and attention mechanism optimization, which can significantly accelerate transformer models. Inference optimization concludes the list of model adaptation techniques covered in this book. The next chapter will explore how to integrate these techniques into a cohesive system. 448, Chapter 9, Inference Optimization. Chapter 10, AI Engineering Architecture and User Feedback. So far, this book has covered a wide range of techniques to adapt foundation models to specific applications. This chapter will discuss how to bring these techniques together to build successful products. Given the wide range of AI engineering techniques and tools available, selecting the right ones can feel overwhelming. To simplify this process, this chapter takes a grad UAL approach. It starts with the simplest architecture for a foundation model applica tie-in, highlights the challenges of that architecture, and gradually adds components to address them. We can spend eternity reasoning about how to build a successful application, but the only way to find out if an application actually achieves its goal is to put it in front of users. User feedback has always been invaluable for guiding product development, but for AI applications, user feedback has an even more crucial role as a data source for improving models. The conversational interface makes it easier for users to give feedback but harder for developers to extract signals. This chapter will discuss different types of conversational AI feedback and how to design a system to collect the right feedback without hurting user experience. AI engineering architecture. A full-fledged AI architecture can be complex. This section follows the process that a team might follow in production, starting with the simplest architecture and progressively adding more components. Despite the diversity of AI applications, they share many common components. The architecture proposed here has been validated at 449. Multiple companies to be general for a wide range of applications, but certain applications might deviate. In its simplest form, your application receives a query and sends it to the model. The model generates a response, which is returned to the user, as shown in Figure 10.1. There is no context augmentation, no guardrails, and no optimization. The Model API box refers to both third-party APIs, e.g., OpenAI, Google, Anthropic, and self-hosted models. Building an inference server for self-hosted models is discussed in Chapter 9. Figure 10.1. The simplest architecture for running an AI application. From this simple architecture, you can add more components as needs arise. The process might look as follows. 1. Enhance context input into a model by giving the model access to external data sources and tools for information gathering. 2. Put in guardrails to protect your system and your users. 3. Add model router and gateway to support complex pipelines and add more security. 4. Optimize for latency and costs with caching. 5. Add complex logic and write actions to maximize your system's capabilities. This chapter follows the progression I commonly see in production. However, everyone's needs are different. You should follow the order that makes the most sense for your application. Monitoring and observability, which are integral to any application for quality control and performance improvement, will be discussed at the end of this process. Orchestration, chaining all these components together, will be discussed after that. Step 1. Enhance context. The initial expansion of a platform usually involves adding mechanisms to allow the system to construct the relevant context needed by the model to answer each query. As discussed in Chapter 6, context can be constructed through various retrieval mechanisms, including text retrieval, image retrieval, and tabular data retrieval. 450 Chapter 10, AI Engineering Architecture and User Feedback. Context can also be augmented using tools that allow the model to automatically gather information through APIs such as web search, news, weather, events, etc. Context construction is like feature engineering for foundation models. It gives the model the necessary information to produce an output. Due to its central role in a system's output quality, context construction is almost universally supported by model API providers. For example, providers like OpenAI, Claude, and Gemini allow users to upload files and allow their models to use tools. However, just like models differ in their capabilities, these providers differ in their context construction support. For example, they might have limitations on what types of documents and how many you can upload. A specialized RAG solution might let you upload as many documents as your vector database can accommodate, but a generic model API might let you upload only a small number of documents. Different frameworks also differ in their retrieval algorithms and other retrieval configurations, like chunk sizes. Similarly, for tool use, solutions also differ in the types of tools they support and the modes of execution, such as whether they support parallel function execution or long-running jobs. With context construction, the architecture now looks like Figure 10.2. Figure 10.2. A platform architecture with context construction. Step 2. Put in guardrails. Guardrails help mitigate risks and protect you and your users. They should be placed whenever there are exposures to risks. In general, they can be categorized into guardrails around inputs and outputs. Input guardrails typically protect against two types of risks: leaking private Informa tie-in to external APIs and executing bad prompts that compromise your system. AI Engineering Architecture 451. An example is when a Samsung employee puts Samsung's proprietary information into ChatGPT, accidentally leaking the company's secrets. Chapter 5 discusses many different ways attackers can exploit an application through prompt hacks and how to defend your application against them. While you can mitigate risks, they can never be fully eliminated, due to the inherent nature of how models generate responses as well as unavoidable human failures. Leaking private information to external APIs is a risk specific to using external model APIs when you need to send your data outside your organization. This might happen for many reasons, including the following: an employee copies the company's secret or a user's private information into a prompt and sends it to a third-party API. An application developer puts the company's internal policies and data into the application's system prompt. A tool retrieves private information from an internal database and adds it to the context. There's no airtight way to eliminate potential leaks when using third-party APIs. However, you can mitigate them with guardrails. You can use one of the many available tools that automatically detect sensitive data. What sensitive data to detect is specified by you. Common sensitive data classes are the following: personal information, ID numbers, phone numbers, bank accounts, human faces, specific keywords and phrases associated with the company's intellectual property or privileged information. Many sensitive data detection tools use AI to identify potentially sensitive information, such as determining if a string resembles a valid home address. If a query is found to contain sensitive information, you have two options.